Alright, so before we move on to talking about how the nucleophile affects things, I want to address sort of the last point of the name of the reaction, SN2. So the S and the N, as we've already stated, should be fairly self-explanatory. Substitution and nucleophilic. But what does the 2 mean? Well, we said it stands for bimolecular. What does that mean? Well, this is referring to the rate law. If you recall from general chemistry that for any reaction we determine the rate law based on the rate determining step or the slow step. Well, in an SN2 reaction, there is only one step. So that one and only step is the rate determining step. And for the rate determining step of an SN2 reaction, the rate looks like rate is equal to rate constant times the alkyl halide or the electrophile times the concentration of the nucleophile. So how many species are involved in the rate determining step? 2. Or in other words, the rate determining step is bimolecular. So if you've noticed, we've also, although we haven't discussed it yet, we have a reaction known as an SN1. Does that mean that the SN1 is only going to have one species in the rate determining step? That's exactly what we'll see. Alright, now we've talked about how sterics can affect an SN2 reaction. So the next thing we'll talk about is how the nucleophile affects it. So we already know that there's a lot of interplay between a nucleophile and a base. And anything that can function as a base can often be a nucleophile. But that doesn't mean the behaviors are the same. Recall that we measure base or basicity by the pKa of the conjugate acid. Well, nucleophilicity, while again it does have some similarities, isn't the same. How do we measure nucleophilicity? Well, it's measured by the reaction rate in an SN2 reaction. So in other words, what someone did was they took a fairly simple electrophile, something like methyl iodide, and they reacted a whole bunch of nucleophiles with it and measured the rates. And then they used that to come up with a scale. So again, as we've said, basicity and nucleophilicity are not the same. And here's a way that we can see that. Let's look at the following example. So here's hydroxide and iodide. So first we can look at the pKa's of their conjugate acids. For hydroxide, the conjugate acid is water, and water has a pKa of 16, approximately. Whereas the conjugate acid of iodide is HI. HI has a pKa of approximately -10. So given that HI is a stronger acid, and by quite a bit, that tells us that the conjugate base of HI, I-, is a weaker base. So if we're comparing acid or base strength for hydroxide and iodide, hydroxide is the stronger base. And again, it's not close at all. And just to go through that again, HI is the stronger acid, which means its conjugate base is weaker. In comparison, water is a weaker acid, which means that its conjugate base, hydroxide, is a stronger base. Now, we can also look at something known as the Swain-Scott parameter. And this will be the first and only time that I mention this term. Basically, the Swain-Scott parameter is what I was talking about a few minutes ago. It was a way to measure how strong of a nucleophile, a scale to measure how good of a nucleophile something is. Well, if we look at both hydroxide, which has a Swain-Scott parameter of 4.2, and iodide, which has a parameter of 5.04, we see that iodide is the stronger nucleophile. So both of these compounds, hydroxide and iodide, can function as nucleophiles. But the message I want you to take home from this page is that hydroxide is a stronger base when comparing to iodide, while iodide is the better nucleophile. So are there trends that we can look at that will allow us to predict nucleophilicity? The answer is yes. They might not be as good or as, sort of simple to follow as other trends we've looked at in this course, but there are some general trends. The first one is negative is going to be better than neutral. So a negative nucleophile is always better than its neutral counterpart. For example, if we look at water, how do we make water negative? We take away a hydrogen. So water is the neutral molecule, and its negative counterpart is hydroxide. Same thing, NH2 minus. Its neutral counterpart would be NH3. What we're saying in a case like this, where we go from a neutral compound to its anion, is the negative or the anion will always be the better nucleophile. Second trend is nucleophilicity, and the ability of something to function as a nucleophile. In general, increases going down the periodic table. So for example, F minus, Cl minus, Br minus, I minus, As we go down that column, nucleophilicity increases. Step number 3. If we have a group of nucleophiles where in each case the nucleophilic atom is the same, such as these 4. So for each of these 4 nucleophiles, the nucleophilic atom is the oxygen. Because it's oxygen in every single case, the nucleophilicity and basicity will parallel each other. And so we can look at the pKa's of the conjugate acids. And we'll see for this group, again, because it's oxygen in every case, as the pKa goes down, that means the acid becomes stronger, the base becomes weaker, and the nucleophile becomes weaker. But again, this is only when the nucleophilic atom is the same. Once your nucleophilic atom starts to change what it is, then you can't use basicity to make these predictions. So the overall effect for an SN2 reaction is this. For an SN2 reaction, a better nucleophile or a higher concentration of a nucleophile will always, this is one of the rare times we use that word, increase the reaction rate.